Simon's algorithm came out, just a little while after the Deutsch-Jozsa algorithm, which I described last time. And you can see how, that Simon's algorithm is somewhat built along the same lines as the Deutsch-Jozsa algorithm. On the other hand, it solves a problem on quantum computers that's exponentially faster than the best algorithm on classical computers, whereas the Deutsch-Jozsa algorithm, the problem that was solved, could be solved just as easily on classical computers if you were allowed a probabilistic algorithm. And the Simon's algorithm is not that far, in some sense, from the factoring algorithm, which we're doing next. So by seeing how Simon's algorithm works, you'll be prepared to see how the factoring algorithm works. The factoring algorithm is quite a little bit more complicated, but it has, the basic lines. It runs along the same lines. So what does Simon's algorithm do? Well, it solves Simon's problem. So given, and Simon's problem is something that may be a little bit non-intuitive, and which certainly is not appear anywhere else. So we'll spend a few minutes on Simon's problem so that you all understand it before I go into the algorithm. So the problem is, given f, so this is another oracle function as a black box. F is either 1 to 1 or 2 to 1 with f of x equals f of x plus c. So this is another promise problem. You're given that f is either one of these, or either this case or this case. And what you're supposed to do is you're supposed to tell which is which. Tell which. And we might as well ask you to find C, because both Simon's algorithm and any classical algorithm for this problem have to work by finding C. Oops. So let's do an example. F maps 0, 0 to 0, 1, 0, 1 to 1, 1, 1, 0 to 1, 1, and 1, 1 to 0, 1. So can anybody tell me whether f is 2 to 1 or 1 to 1? 2 to 1. Very good. And can anybody tell me what C is? F of x equals f of x plus c. So what's C here? I should say x plus in terms of exclusive R. Yes? 1, 1, because you add 1, 1, you take 0, 0, you get 0, 1. Now you add 1, 1, binary with no carry. That's what x exclusive R means. You get 1, 1. Now, similarly here, you take 0, 1, and you add 1, 1 to it, you get 1, 0. So these two are related by C, and these two differ by C. So how well can you do classically? Well, I thought we would have a game with the class, and you query inputs, and I tell you what the values of f are. Now, first, does it make any difference at all which input is the first one you query? No, it doesn't, because, well, basically because everything's symmetric, and I seem to have done something very wrong here. There we go. So, which one shall we query first? Any volunteers? What?
All zeros.
All zeros. OK. I'm not going to write these in binary because it's easier to work in decimal. What should we do next?
0, 0, 0, 1.
Sure. That gives us 6. Anyone else? Anything next?
0, 0, 1, 0.
OK. That gives you 5. Another one?
All 1.
All ones. Excellent. That gives you 9. Another one?
1 and 3 zeros.
1 and 3 zeros. OK, let's see.
Top right, sorry.
1 and 3 zeros. OK. That gives you 8. Well, it's pretty clear we're not going to get anywhere until we find 2 that match. So another one?
1, 1, 0, 0.
1, 1, 0, 0. 11. Another one?
0, 1, 0, 0.
0, 1, 0, 0. Well, 0, 1, 0, 0. 6. OK, so we're done. We have 2 6s. And 0, 0, 0, 1 minus or plus, it doesn't matter, 0, 1, 0, 0 equals c equals 0, 1, 0, 1. So this is the value of c. This function happens to be 2 to 1. And we're done. So this is how all classical algorithms work. Yeah?
Wouldn't you have to check the rest of the ones that it's not the same value difference?
Well, we're promised that f is either 1 to 1 or 2 to 1 with f of x equal f of x plus c. So we don't care if our algorithm fails miserably for any other functions. We just want it to work in these 2 cases.